Okay, welcome. This is going to be actually, is it 403 or 413? I think it's 413. You'll have an auspicious start of correcting right from the beginning. Okay, so this is going to be pseudorandomness.
What is CSS?
So CSS is the Computer and System Sciences subject board. Every subject board has a code. So biology or physics, etc., will be different. The last .1 refers to the Mumbai campus.
Oh,
Yeah, .2 is probably some other TIFR campus. .0 is a pan TIFR thing, and the only course I know that has a .0 thing was the machine learning introductory machine learning course. Yeah, at least. Okay, so let me get some administrivia thing out of the way first. So this is going to be like an advanced course. So in the sense that it's not suitable for qualifiers in some sense. So not going to be suitable for qualifiers, and as a result, I am not expected to have an exam. So I'm not going to be having an exam. It makes my life easy. So we'll have about 4 problem sets. And depending on interest, etc., we could have some sort of project presentations or something at the end. But if there are a lot of people who are crediting it, then it will mean that there's going to be a lot of project presentations, and maybe that's not ideal. We'll take a call about that part towards the end. But at the moment, I'm mentally thinking of as the entire evaluation just being based on problem sets. Those of you who are auditing or who are participating over Zoom, etc., you are still welcome to submit your. If anyone who submits that problem set, I will evaluate. What that evaluation means to you is up to you. I mean, you can do whatever you want with it. But those who are crediting it in TIFR, of course, you get a grade for it, etc. And then with respect to the main reference, there is this really nice monograph by Salil Vadan called Pseudorandomness. If you go to the course webpage, which is on my homepage and so on, you will find a link to this monograph. I think it's freely downloadable for anyone. I mean, if you need like a soft copy of it or something, please send me an email and I'll be happy to share one with you. Okay, and one tricky thing, this time I'm going to try and use this thing called Piazza. It's some course management system. Apparently it's supposed to make life easier, except that I've not used Piazza before. So I'm going to try and use it. So the way apparently Piazza works is that I need to enroll students who are interested. So there's a bunch of emails that you have sent me so far. So the default thing would be to enroll that, but maybe you have a slightly different email that you prefer for Piazza or something. So in any case, basically at the end of today's lecture and those on Zoom, etc., just write your preferred Piazza email over chat there, or those who are here in person, just send me an email with what your preferred Piazza email is. And by the end of the day, I'll just add all of you to the course. Okay, so that's about it. So today's lecture is going to be very introductory. I mean, there is very little concrete content that I'm going to do. It's mostly to give a sense of what this course is about, because pseudorandomness it's a very vague and unspecified term, and it's going to be very, very context dependent. I mean, to me, it's more like it's one of these things that sort of shape the way you start thinking about problems. But pseudorandomness by itself doesn't really have a definition unless you put it in a certain context. And the point of the course is to see different guises in which this concept of pseudorandomness appears in complexity or CS in general. And it's just that there won't be any specific definition. It is just that it's a word like regular. I mean, regular could mean different things depending on what context you're working on. Okay, it's just a very vague term. Okay, so what is pseudorandomness? And in some sense, I'm just going to say the pseudo here refers to something like behaves like. Okay, and so basically the entire context is going to be, there are going to be situations where randomness is useful, and we are going to try and see, can we get that same utility without using randomness? We're going to try and work with something that sort of behaves like random stuff, but it's not really random. Okay, and maybe see if we can do that. So this is what pseudorandomness sort of means. But in some sense, the ambitious goal is going to be to either reduce, or if you are super efficient, completely eliminate the need for randomness in computational tasks. Okay, and this is going to be an ambitious goal in the sense that we are actually not going to be successful in this goal in general. I mean, it's sort of too good to be true. There are some situations where randomness does seem to help a lot. But it's a very useful perspective to have, because every time you encounter a place where randomness is used, it helps to think in these ways. And we will sort of see that these ideas here are sort of ubiquitous. I mean, in the sense that it sort of shows up in so many varied fields in CS. And the goal of this course is to just give you a glimpse of various examples of this. And just get more used to thinking in terms of what really about randomness did we use in this particular application? And can I get away with it by using something else, which is not quite random, but has the same behavior? As far as this is concerned, it has the same behavior. That's going to be the rough goal. So before we proceed to how we eliminate randomness, it would make sense to first ask, what are some examples of situations where randomness has been super useful? Okay, and then we can try and say, okay, here are some concrete tasks. In these concrete tasks, can I get rid of randomness somehow? Or maybe minimize the amount of randomness that's being used. So I'm just curious. So what are some randomized algorithms that you can think of? Things that come to your mind when someone says randomness.
Primarily.
So primarity is one amazing example. Anything else? Yeah, any crypto. I think I need, going from the welcome, you should be careful and say that any cryptographic algorithm, because crypto means a lot of things.
In
That also uses a lot of. So what are other situations?
Like distributed algorithms will have like the symmetric weighting sort of stuff.
Okay, so it shows up in distributed algorithms. I was expecting Shrija to use good. Okay, so we have already, just among these examples, you can already see that there are some situations where, for example, primality testing, you know that there are algorithms that don't use randomness at all. So that has been successfully de-randomized in some sense. And somehow it feels like cryptography randomness is essential. In fact, that's the only thing that separates the actual user from the adversary. I mean, what random coins I tossed is the only thing you don't know. So if that is done deterministically, it feels like the whole thing sort of breaks down. Okay. Distributed algorithms, it depends on what sort of algorithms we have, but you can imagine that there are some algorithms that possibly one can get around without using randomness, in some places you can't. And communication complexity is going to be one of the examples that we will see here, where randomness seems to be essential. There are certain tasks that you can do substantially better when you have access to randomness compared to when you don't have access to randomness. Okay. So what I'm going to do today is give you a few instances when randomness is used and try and ask, are these situations where we can get rid of randomness? Are these situations where we can't get rid of randomness? And slowly explore this and set up the background to come up with some general enough definitions that we can work with the rest of the course and focus on those. But these are going to be, in some sense, what you should, concrete instantiations you should have in mind. When we are looking at these more general frameworks, in some sense, you should tell yourself, that's what I actually want to solve. We are trying to establish the language to get to that point. Okay, we're just trying to understand how do we need to concretize the road towards that. Okay, so I want to start with randomness and communication complexity, because in some sense this I feel is one of the starkest examples of randomness being super useful. Okay, and I don't expect people to have a lot of background on this, so I'll just tell you what it is. So typically in communication complexity, you're interested in computing two input function. Okay, and I made life simple and sort of said that the two inputs at the end of it, I just need to say yes or no, or 0 or 1. So okay, it's a Boolean valued function, and the inputs we just call sigma star from some alphabet sigma. You might as well think of sigma as just being 0, 1, so it's like strings, maybe strings of length n or whatever. Okay, and the setup is that there are two parties that are usually called Alice and Bob. And Alice is given an input x, Bob is given an input y, and their goal is to compute this joint function f of x comma y. So they both only possess a part of the input. So just by x alone, maybe the function is something that, I mean, you don't know what the function value is going to be just by looking at x. It's something that depends on both x and y. And I'm going to assume that Alice and Bob are like, they have access to any sort of computational machinery that they want. So if they want to do some complicated computation with respect to x, I'm not going to charge them for it. What I am going to charge them is their communication between them. So the main measure of interest is amount of communication. Okay, so obviously a stupid protocol here is that Alice could just say, hey, my first message could just be x is the input I received, and Bob on his side just computes f of x comma y. So that's always a thing that you can do. So the naive protocol is going to be n bits, because you can always do it with n bits. Alice just sends, I'm going to by default assume n refers to the input size. So in this case, the length of x and y. Okay, but we would want to know, maybe there are some situations in which for certain kinds of functions where you can get away with sending less, okay, communicating less, and that's sort of what we're going to focus on. And there's one very nice function that's going to illustrate the power of randomness, which is this equality. Okay, Alice and Bob has two inputs x and y, and all they want to check, do they have the same input or not? Okay, so if they have the same input, I want to output 1. If they have two different inputs, I want to output 0. This is all I want to check. And for people who have not taken a communication complexity course, etc., what would your guess be for if you're not allowed to use randomness? Okay, Alice and Bob have to talk to each other, and at the end of it, figure out whether x and y are the same or not. How many bits of communication do you think you need? Yeah, it sort of feels like, unless what else can you do besides sending x across, right? I mean, like, it feels like if there is some particular bit of x that I don't talk about, maybe I can adversarially set up a particular input such that, the inputs were different, but I somehow made them believe that the inputs were the same. This needs to be formalized, but turns out you can, and you can actually show that the communication complexity is actually n. I mean, I've written omega n for safety purposes, but it's actually n. This is something that you do in maybe your first or the second lecture of a communication complexity course. This is one of the first lower bounds you show, that equality is something that requires n bits of communication. Okay, and just you putting a deterministic on top just to indicate that if we talk about the deterministic communication complexity of the equality function, it seems to require n bits. Okay, and now the question is, what can you do if you have access to randomness? Okay, so I'm going to give a protocol for those who are familiar with it. This is the private point protocol. So what I'm going to do is the following. I'm going to just imagine that 0, 1 to the n, which is where Alice and Bob's inputs came from. I just think of it as an n-bit integer. So it's some integer between 0 and 2 bar n. Okay, so here's what Alice is going to do. So let's say P2n is the first 2n primes. Okay, just collect the first 2n primes. Alice computes it on her side and just keeps it with her. And what she's going to do, she's going to pick a p uniformly at random from p to n. Okay, and just send across whatever prime was chosen along with what is the residue of my number mod p. It's like maybe the prime chosen was 7 and Alice just sends across, hey, I chose 7 and my number, if I divide by 7, has a remainder of, I don't know, 4. That's what Alice sends across. And Bob just basically checks if y mod p equals x mod p. If this is the case, then Bob, obviously if x and y were the same, then of course these two better match up. Okay, but if x and y are different, the hope is that this p will tell them apart. Okay, and maybe if Bob is not satisfied with one such check, maybe you run it, I don't know, a few times or whatever. Okay, so let's just get a sense of, let's imagine just running it once for now. How much communication did we actually end up using? So we pick the first 2n primes. And the first 2n primes is roughly what, like n log n sized or something. That's the magnitude of these primes. So to send p across, I just need to spend log n bits. Okay, and the residue is also somewhere between 0 and p. So I'm basically sending 2 log n bits. Okay, and at the end of it, maybe Bob decides, okay, the x and y are equal or not equal. So we really need to get a sense of, if x and y are equal, obviously they return the right value. Okay, but if x and y are not equal, I somehow want to say that there is a decent chance with which they will say, no, these two numbers are actually different. Okay, so what prime would be bad for this situation? Like what are situations where x and y are actually different, but if somehow Bob mistakenly thinks that x and y are the same because maybe the residues match up?
When p will be less than x.
Sorry?
When p is less than
P will almost always be less than x because x is in a massive range. It's like all the way till 2 power n. And p is like about n log n or something. Like p is really small.
P divides x minus 5.
Yeah. So the problem is if x mod p and y mod p will be the same if p happens to divide x minus y. Okay. So p divides x minus y is the bad case. Okay, but x is a number between 1 and 2 to the n. Y is a number between 1 and 2 to the n. So the difference is some number between 1 and 2 to the n. How many different prime factors can it have? Every prime factor is at least 2. So they certainly can't have more than n prime factors. Right? But x minus y has at most n prime factors. You can say something better, but I'm just being really sloppy here, just to give an obvious bump. That's it. One can be a little cleverer here, but I don't know. Okay. But I chose the first 2n numbers. There are at most n bad primes. So with probability half, I will choose a number which is not a bad prime. Okay. So if you're not satisfied with it, okay, run it 100 times and whatever. So strangely, so therefore, the communication complexity of the equality function in the randomized setting, this is actually just order log n. That is, we just gave a protocol that gets it right with high probability. In this case, the error was like half, but you can make it better if you want. Okay, and it says that with a little bit of randomness, and if you're willing to tolerate some error, you can do substantially better than what you could when you didn't have access to random. Okay, so I'll also mention that this was what is called the private coins protocol, in the sense that I'm not assuming that Alice and Bob share any amount of randomness. If you actually assume that Alice and Bob both share an amount of randomness, in the sense that they can both look at the sky, they can both see TV where random nonsense is being spoken, etc., then you can actually come up with a constant sized protocol, the communication complexity being just constant. Okay, but anyway, but at least this tells you the sharp contrast as to what you can do with randomness and what you can do without. Okay, so here was a concrete example where randomness does seem to make a big difference. Okay, so now I'm going to give you, this is also one of my very, like this algorithm a lot. And this is apparently Prahlad's favorite randomness algorithm. So I'm going to tell you a little bit about it and show the power of randomness here. And this requires a little bit of field or whatever, at least just modulo P stuff, which I'm going to tell you right now. Okay, so there is this thing called FP that shows up often, which is just the set of the residues modulo P, the 0, 1, 2, all the way to P minus 1. And you can always add these numbers, multiply these numbers, etc. But every time you add or multiply or whatever, you again take its residue mod P. Okay, and the nice thing about it is you can also divide by anything non-zero. Okay, that's one thing that happens. And we're going to focus on this stupid operation, which is just taking a number x and looking at the square of that number. Like for example, if p was 7 and if x was 3, then 3 squared is 9, but 9 mod 7 is 2. So I'm going to tell myself 3 squared equals 2 in FP. Okay, so let's draw a picture as to what this looks like. Obviously, if I start out with 0 and I square 0, I'm going to get 0. And notice, because p is a prime, nothing else when I square will give me 0. Because if something was non-zero to begin with, when I square stuff, it's going to remain non-zero. Okay, so the only thing that maps to, by the way, this is just a picture. I'm just written FP here and FP here, and what the function does when you square stuff. Okay. But on the other hand, both plus a and minus a will both get mapped to whatever a squared is. Okay, so you have this nice, whatever, 2 to 1 map. Okay, and as you can imagine, so the things that are in the range, besides 0 for some technical reasons, they are called quadratic residues, in the sense that there is something you can square to get whatever is present here. Okay, this entire set of things, it's in the range of the squaring operation, and they are therefore called quadratic residues. And because it's a 2 to 1 map, obviously there's going to be things that you cannot obtain, because clearly it's not an injective map here. So there are some things that are not going to be in the image, and they are called quadratic non-residues. Okay, how many quadratic residues will be there? Yeah, so basically it's a 2 to 1 map. Every guy only has two pre-images, plus a and minus thing. So besides the 0, there were p minus 1 other elements, and they will all get bunched up into pairs, and therefore this is going to be p minus 1 p2. And therefore the quadratic non-residues is also the remaining p minus 1 p2. Of course, for any self-respecting prime, that prime should not be 2. So I'm going to assume that this p is a large prime, etc. So it's an odd number. So p minus 1 by 2, etc. is actually an integer. Okay. So this was just the background. So here is the computational task. I give you a prime p, which you should think of as a large prime, and I give you an alpha. Okay. I want you to either compute a square root of it, that is, compute some beta such that beta squared equals alpha, or you basically return bottom. That is, if there is no square root for beta, square root of alpha, I want you to just return bottom or something. Okay, this is the computational task. You are given some alpha, which could be a quadratic residue or a quadratic non-residue. If it is a quadratic residue, I expect you to return a square root. I mean, okay, I wrote it in a weird way. You can't always return bottom. I mean, when it is a quadratic residue, I want you to return a beta such that beta squared equals alpha. Okay, and this is the computational task we have at hand. How many of you have seen this before?
Okay, can you simply check alpha power p minus 1 by 2?
Sorry?
Checking can be done easily.
Yeah, whether or not alpha is a quadratic residue. Okay, so that was my next thing, which is, so turns out there is a good fact to have in mind. I'm not going to prove it right now, but intuitively it should sort of make sense, in the sense that all I want to say is like, sorry. So if you look at product of all quadratic residues. Just look at x minus alpha and multiply all of them together. It magically simplifies into this one expression. X bar p minus 1 by 2. Notice that the degree is slightly matched up. The left hand side has, there are p minus 1 by 2 quadratic residues. So therefore the left hand side has degree p minus 1 by 2 and it matches up correctly. The other way to interpret it as is what Srijato said, which is that if alpha is a quadratic residue, plugging x equal to alpha makes the left hand side 0. So it should also make the right hand side 0. Which means another way to say it is something is a quadratic residue if and only if that power p minus 1 by 2 happens to be equal to 1. So you can think of that as a criteria of whether or not something is a quadratic residue. Okay. So now I'm going to give you an algorithm. Okay. So I have a polynomial. I'm given an alpha, so I'm going to look at the polynomial x squared minus alpha. Okay. I don't know what beta is, but whatever that beta is, this is supposed to split as x minus beta into x plus beta. But I don't know what beta is. That's what I'm trying to get a hands on. Okay. Here is some wishful thinking. Suppose it were the case that beta happens to be a quadratic residue, but minus beta is not a quadratic residue. Just by chance. Okay, this need not be the case. Yeah, okay. But suppose it were the case that beta, one of them happens to be a quadratic residue and the other one is not a quadratic residue. Then I want to claim there is a very simple algorithm to extract out this beta. And someone say, how? Excellent. So if exactly one of beta or minus beta is a quadratic residue, then the GCD of x squared minus alpha with x bar p minus 1 by 2 minus 1.
Actually, there is an issue here because this degree is very high.
Yeah, I'll come to that. Hold that thought. So this should basically give, let's say, for example, if x minus beta is the one that is a quadratic residue, I'll end up getting x minus beta. Why? Among this and this, the only thing that's common there is the whatever was the quadratic residue. So if one of them was a residue and the other one was not, one of them is not a factor here. So that part sort of gets filtered out. Okay. So in this case, seems to be a very clean thing. As Srijato pointed out, right now the degree here seems to be very large because I think of p as a very large number. But fortunately, because it looks like x power a very large thing, there are these repeated squaring tricks you can do to get around this.
So actually, after the first iteration only.
Yeah, so basically, how do you compute the GCD algorithm? GCD of f and g is the same as GCD of f and g mod f. And g mod f will just crash the degree to a linear thing anyway. So you don't need to
evaluate the right hand side modulo the left hand side.
That's it. So this gives a very simple algorithm. Of course, this works only if we are in this magical situation where one of the betas happens to be a root, one of the betas happens to be a quadratic residue, and the other beta is not a quadratic residue. Okay, so the question is, how do you do to fix it? And here is a beautiful idea, which is what you do is instead the following. You just choose A and B at random. And look at the polynomial where you're making this change of basis in some sense. You just replace x with ax plus b. Okay, it's the same equation. Previously, it was x squared minus alpha. And now it's going to be ax plus b minus alpha. Ax plus b the whole squared minus alpha. Okay. Now, previously, the roots were, it was actually x minus beta into x plus beta. So the roots now will basically be a beta plus b and minus of a beta plus b. Because all I'm doing is a change of basis. Okay, and I'm being sloppy here. So the observation is that if A A and B are uniformly chosen at random from FP, then A beta plus B and A into minus beta plus B are two independent uniform elements in FP. So this is something we'll actually deal with in more detail later on. But intuitively, it feels like beta and minus beta were somehow felt they're correlated, because they both seem like one of them was a negative of the other. But the moment you do A alpha plus B, it somehow feels like you can map them to any 2 points. And if you think of A and B as chosen at random, it basically goes to any 2 points. So which means now with height, the probability that either both of them are quadratic residues or both of them are quadratic non-residues is just a half. Because it's like as if they got randomly shot into FP. So the chance that they both fell into the same bucket is going to be like about half. Okay. So this algorithm, all it does is it does the same thing and just undoes the whatever, the basis change. You run the previous algorithm after a basis change, and then you undo that basis. It's a very simple algorithm. It's not hard to analyze with some very basic properties, etc. But I mean, this is, as far as I know, this is one of the only algorithms we know of where there is a randomized algorithm that makes no error. So there's a class called ZPP, or if you think of it, it's in RP intersect co-RP. Okay. So there is an expected polynomial time algorithm that makes no error. Notice that when I output a number, I'm always going to output the right square root. The thing is, if I fail, I just try it again and again until I succeed. Okay. And this is an algorithm that is known to be in this class ZPP. And till date, we do not know of a deterministic algorithm for it. It's a surprisingly simple algorithm, but somehow this one thing that seemed to have evaded all attempts to try and de-randomize this.
So what is the best one deterministic running time?
I think basically like these number field sieve type things, the sense that if you can do discrete log in FP, you can do
You
this.
can backward experiment as probabilistically.
No, I'm talking about deterministic.
Oh.
Deterministic. Deterministic, I mean, like there are these deterministic, whatever, discrete log type variants. I think that's the only thing. I mean, I think that also is heuristic. I don't know if there are concrete ones there. So anyway, just wanted to point out that here is an example of an algorithm that is a very simple to explain randomized algorithm, and somehow we have no clue of how to come up with a deterministic analog of this.
This is a special case of the polynomial factorization.
Yeah, it's just factorizing quadratics in some sense.
Maybe those have.
Yeah, even though I just picked up the simplest example I know of, that where there is a randomized algorithm that works, but somehow we don't know.
What happens if alpha is a quadratic non-residual?
Oh, so the thing is, maybe what I should have said is the first thing you do is you check if alpha per p minus 1 by 2 is 1. If you get -1, you return bottom. Otherwise, you do this nonsense. Okay, so I should have mentioned that. Okay, so good. So this is what this is. So now that I've given you some sense, and I want to sort of say, how do we propose to eliminate randomness in general? Like, okay, we saw some examples of randomized algorithms. They seem to be doing quite remarkably. What is the general strategy? Okay, so here is a, sorry?
No, just another very interesting thing which we don't know to de-randomize. And very simple to state is generate a prime
between n and 2n. Yeah. So yeah, actually this one can be phrased as a so but that is also another thing which we don't know how to. Huh? Sorry? It's not in the sense that both of these are phrased as search problems, but they can be phrased as decision problems also if you want. But anyway, okay. So how do we propose to eliminate randomness? So here is a sequence of digits.
That's a little more vexing because in that there the randomized algorithm is pretty obvious.
Yeah. Yeah, you just pick something at random from the interval and then check. Yeah. Okay. So here is a sequence of digits. And is this a random sequence? I mean, of course, we don't, I mean, there's nothing probabilistic here. I've written something deterministically. But intuitively, does it feel like a random sequence? Or is there a pattern that any of you notice?
There is no link.
Huh?
There is no link.
There are a few 8s. There are a couple of 8s or something.
There is no zero.
Oh, there's no 0 surprise. Okay. But maybe this will help.
By that time, 0 was still not invented.
Does this help? Okay. So these are basically the first few digits of pi. And I had just removed 3.1 because otherwise it would have been so just to throw you off a little bit. Okay. So in the sense that, okay, it's not a random sequence because it's very deterministic in that sense. But I think the right question to ask instead is the following. Suppose you came up with some randomized algorithm. And in your randomized algorithm, every once in a while, it will need a random bit. Let's say for simplicity, it needs a random digit. Okay. And suppose every time it asks for a random digit, you just feed the next digit of pi. Okay. I mean, do you expect your algorithm to suddenly just completely break apart? I mean, so that's the sort of question we are going to be asking. This is that, yes, it is true that the above thing is not a random sequence. But the point is, as far as this computational task is concerned, whenever it asks for a random sequence, suppose I start feeding in the next digits of pi, do I expect this algorithm to just behave so differently compared to what it would have had I fed it truly random bits? Okay, that's going to be the focus of what pseudorandomness is. In the sense that we're going to sort of say, whenever we say something is pseudorandom, it's with respect to a particular context. So we would want to know, look, this algorithm is expecting random bits. And if I give it random bits, I know its behavior is going to be something I like. But can I get the same behavior of this algorithm by somehow not giving it random bits and giving it something else, which perhaps I came up with deterministically? Because intuitively, you would want to say that, what the hell will pi's digits have anything to do with the primality test? I mean, it somehow feels like, there should be sort of disconnected, and hopefully this will just work for this thing, but proving it is going to be difficult. So we're going to try, and this is the rough idea, I mean, like sort of setup we're going to try and have in mind. And this is that, this randomized algorithm needs random bits. But can I somehow fool it into thinking that whatever I'm giving it is actually random? Okay. And so as far as whatever you're feeding in looks random to that algorithm, in the sense that it's not able to change its behavior because it realizes, aha, you started giving me digits of pi. I mean, unless your randomized algorithm is first going to check if the random bits is received looks like pi or not, and then does something nonsensical. It feels like it should just work. So that's what we're going to try and focus on. Okay. So the goal throughout this course is going to be to look at specific instances where there is a particular algorithm or a particular task that we are interested in. And we know how this task works when we feed purely random bits. And we are going to ask, can I generate possibly deterministic sequences, or maybe sequences that uses far fewer randomness? Somehow they're very correlated with each other, etc. But as far as this algorithm is concerned, it's not able to tell us. So its behavior is roughly the same. Okay, so that's going to be the goal. And this is the sense in which we're going to start talking about what we are going to call pseudorandom objects. And again, this is very context specific. But intuitively speaking, a pseudorandom object is something that seems to share certain properties that a random object would have. So we are going to turn this around and sort of say this algorithm works well with this source of randomness because this is the property of randomness that you actually used. And then we will then say, can I construct deterministic things that have the same property? So that if I now feed that to the algorithm, maybe the algorithm behaves roughly the same. Okay. So that's going to be the goal. And in general, these are pseudorandom objects is a very still a vague term. And we will just see various examples of this. So I'm going to start with some examples, which is like what pseudorandom's graphs are. Okay. By the way, there's no one definition. There are like a gazillion definitions. We are going to see some examples. Okay. First, before we ask what a pseudorandom graph is, we should have a mental model of what is a random graph. Okay. So a standard way of thinking about random graphs is like you just think of it as saying, look, I have n vertices. I need to decide what the edges are. So for every pair of vertices, I'm going to toss a coin that turns up heads with probability P. And if it turns up as heads, I will put that edge. Otherwise, I won't put that edge. And I just do this independently for every edge. Okay. And you can always adjust your P depending on how many edges you sort of want to have. Like if you want your graph to be like, I don't know, roughly degree 100 or something, then you set your P to be like something like 100 over n. Okay, so that roughly among the n rays emanating, potential rays emanating out of this vertex, like some 100 of them will show up on average. Okay, and this is what a random graph is. So it's going to be a roughly 100-degree graph, because you sort of want to say that it's very unlikely that a single vertex somehow a lot of the coin tosses turn up as heads. Maybe it's not 100 degree, certainly not more than 200 degree or something like that. So it's like an approximately 100-degree graph. Okay. Okay. So we can say that, a 100-degree graph is pseudorandom in the sense that the degrees of all the vertices look like what you would have gotten. But that's not particularly interesting. Okay. Now let's ask ourselves, how many triangles will this graph have? So a triangle is just UVW, such that all three are connected to each other. So it should be basically the number of ways of choosing three vertices is n choose 3. And each of the edges will show up with probability P. So the right answer should be something like P cubed times n choose 3. That's the number of triangles you should expect. Now you could ask, can you construct a graph such that the number of triangles is actually this number? A random graph has this number, but no, can you construct a, 100 regular graph or something of that sort, such that it has the right number of triangles? I mean, again, there's nothing special about triangles. Maybe you could change this to squares, or you have some particular shape that you're interested in, and you're just counting how many copies of this shape sort of showed up in my graph. Okay, so depending on that, you could have some. And another thing you sort of have an intuitive sense of is that these are graphs that are really, really well connected. If you think about it, I mean, like, it somehow feels like to go from one vertex to another vertex, you will sort of reach it in about log n steps. We need to sort of see why that is the case, but it somehow feels like a really well connected graph. It has very few edges, by the way. It has only about 100 n edges, but somehow it's super well connected. Okay. So you might want something where, are there deterministic examples of graphs where the degree is very small, but somehow it maybe is super well connected, it maybe has the right number of triangles, or whatever other property, you want these random graphs to satisfy. And these things.
Why is it well connected?
So the intuitive thing is, if you take maybe the first, few log n steps, you don't expect to have, it will sort of look tree-like in some sense. Like in the sense that every time you take if you do a breadth first search in some sense, you will cover a lot of vertices. So in very few steps, you have managed to reach almost a constant sized part of your graph. And somehow repeating this a few steps will tell you that the diameter is very small. Okay. And there are these graphs which are called expanders that basically expand in this sense. In the sense that if you have a small set of vertices, their neighborhood is substantially larger than what you started off with. Okay. And you may have seen in other places that these expanders are ultra useful. Like there's so many places where you just work with an expander and just miraculous things happen. So we're going to spend a fair amount of this course trying to construct expanders, try to see, where these expanders may be used, etc. But you should basically think of it as an expander is a deterministic version of what a random graph looks like. So when I was talking about how pseudorandomness is something that helps you start thinking about things in a slightly different way. Because many times when you think about expanders, you will sort of say, oh, this ought to be true because I expect this to happen when this graph was chosen at random. there are lots of times when you will make these heuristic arguments in your head to sort of say, oh yeah, this should happen because, well, the number of edges going out should be the right number, and so on. You make these vague statements as a heuristic to somehow get an intuition of what is going on. And it can be formalized because an expander does share many of the properties that a random graph is supposed to share. And okay, so we're going to spend a fair amount of time on this. Okay, so the next thing I'm going to think of is just in this big bag of functions from 0, 1 to the n to 0, 1. Okay, and I'm going to pick a function at random. And I want to understand what properties will such a random function have. Okay, so I want to get a sense of what is a pseudorandom function. Okay, that's what we are trying to get a sense of. So let's first ask ourselves, how many different functions are there in this bag? That is, if I look at a set of all possible functions on 0, 1 to n, how many of them are there?
2 power n.
Okay, so it's 2 power 2 power n. Because basically I need to choose some subset of this guy and decide that they are the zeros or they are the ones or something. So I'm looking at all possible subsets of 2 power n elements, so it's 2 power 2 power. Okay. But many times you will be interested in, let's say, computing a function using some small circuit. It's like made up of AND gates and OR gates or whatever gates you care about. Put some connections, etc., etc. And you would want the circuit to be smallish. Think of the size as being, I don't know, n power 5 or n power 10 or something like that. And we could ask, how many circuits do we have of S gates?
Exponential of all of these problems.
Yeah, so it's with the exact number is not going to be very important, but what Sujata said was absolutely correct. So it turns out the right answer is 2 to the order S log S, basically, but I'm just putting S squared for simplicity. But intuitively, you should think of it as one way to convince yourself of this is the following. If you had a circuit with you and you wanted to describe to me what the circuit is, you shouldn't need a lot of information. Right? You should say that, hey, by the way, I picked up this gate, that gate is connected to these gates, etc. So the amount of information you're going to tell me to describe what the circuit is poly in the size. If you think about it, it's just quadratic or something like that. Okay, so therefore the number of different circuits is as much exponential in the communication that you need to have with me. So you can show that it's actually 2 to the order S log S. So now, okay, let's think of S as being, I don't know, n power 5 or n power 10, or maybe even 2 to the n by 100. Okay, notice that this number is much, much larger than this number. Okay, if your S is smallish, there are way more functions than there are circuits of sizes. Which means when you pick a function at random, it's very unlikely that it is computable by a circuit of small size. Okay, so in some sense, so random function is going to be not computable by circuits of size 2 to the substantially smaller than 2 power n. Okay, with very high probability, just because of it's a counting argument. It's just that there are way more functions than there are circuits. Okay, so in other words, hard to compute function, whatever is your notion of hard to compute, in the sense that it cannot be computed by small circuits, etc., is a pseudorandom function, in the sense that that is a property that is shared by what you would have gotten had you picked a random function. So in this very specific context, it shares the property that a random function is expected to share. So in that sense, it's a pseudorandom object. Hard functions are pseudorandom. Okay, now let's look at one other example, which is just collection of strings. Okay, I'm going to choose some bunch of strings on n-bit strings. And let's say I take about, I don't know, 2 to the n by 100 of them. Okay, like a substantially large number of strings. And I want to ask, so let's fix some string x of interest and ask, what is the chance that if I picked another y at random, that this x and y are too close to each other? By the way, this is just Hamming distance in the sense that x and y differ in at most 10 coordinates or something. There's nothing special about 10. You could have put whatever. And what should this number be? Right. So there are n power 10 coordinates on which you could differ. So there are roughly n power 10 ways of choosing. Okay, so it's some rough calculation, and you will get something that looks like n power 10 by 2 pi. So if you expand this out a bit more, and if you now say that, if I picked up a small bag of strings, that is by smallish bag, in the sense that it's like 2 to the n by 100 of them, the chance that 2 of them are very close by is very, very small. I mean, very likely they are going to be sort of spread out. So that they will all be sort of far from each other. Okay, that's one property that a random collection of strings have. Okay, and error correcting codes are a deterministic instantiation of this. When you say that I want an error correcting code, you're looking for a collection of code words that are all spread out. And you want to get a lot of them. Okay. And here is an example where we know that had we picked things at random, it would have had the property we wanted. And the whole subject of error correcting codes is basically to try and find deterministic ways of coming up with these codes that are sort of far apart. Okay. So there are various sort of different things that all seem to be, they have the flavor of pseudorandomness, in the sense that had I picked things at random, I know this property would have been satisfied. And I'm interested in actually picking them deterministically. And the cool part in this course, it will turn out that these different pseudorandom objects are actually connected to each other. One of the things that we will see is that if you have access to an expander, you can use that to build codes. Or if you have access to a hard function, you can use that to build other stuff, and so on. So there's going to be a lot of interconnections between these various notions of pseudorandomness in different fields, and that's sort of what makes this a very nice concept to have in mind, because it shows up in a lot of places, and it's not even disconnected situations where it shows up.
But functionally complexity pretty complex.
Yeah, so there are some, I mean, every time you go from one to the other, there are these extra bells and whistles you need to add. Sometimes the bells and whistles are too heavy, but in general, the intuition works out. So that if you have one, you have another. So there are these things called hash functions and so on. So you can build one using another and stuff like that. Okay, so what I'm going to do is like roughly the first part of the course. We're going to focus on one specific task that will sort of work as a benchmark. Okay, it's a general enough task, and it's like every time we come up with a new construction, we will sort of measure how well it does with respect to this task to get a sense of, are we making progress? Maybe there are some parameters in which we are improving, some parameters that we are not improving, etc. And that task is what is called, these are called samplers. Okay, and the task is the following. Okay, you're given some oracle access to a function. Okay. This function, it takes value 0s at some places, it takes values 1 at some places. Okay. And what I'm interested in is its average. Like, how often does it take the value 1? So this expectation over x is just x is drawn uniformly at random, and I'm asking what's the chance that the probability that f of x is equal to 1. So basically the density of 1s in the function. Okay, we'll call that mu, or mu of f, or whatever. Okay, and what I want is to estimate mu. I am willing to tolerate some accuracy error, and I am willing to have some small chance that your estimate is bad. So what I want is I want to be probably approximately correct. Okay, that is, I want some algorithm which is going to make whatever calls to f at some points that it chooses, etc., etc. And at the end of it must spit out a number. Okay, which we'll call mu hat usually. Mu hat is the estimate that the algorithm A is going to give. And what am I interested in? I want the mu hat, whatever is outputted by the algorithm, to be within the right answer up to an additive error of epsilon. And I'm willing to tolerate a small probability delta where you fail this guarantee. In the sense that what I want is with very high probability, I want you to be within an epsilon of the right answer. Okay, is the question clear? So this in general are called epsilon delta samplers. We will deal with these in more detail in the next class and so on, but I'm just going to give you a sense of just to put this out there so that you know what we are going to use as a benchmark for subsequent things.
So I just had one question.
Yeah.
So this probability is over A. I mean, A is randomized.
Good. Actually, I should have mentioned. So this probability is over choices of A. So the algorithm A might make decisions based on maybe it tosses its own random coins or whatever. That's what the probability is over. Okay, and I want the algorithm to output some estimate of what we use. So it's a rather general sort of function. I mean, like we'll sort of see that if you can solve this problem really well, you can solve a lot of things, because many times what you would want to know is like, how often is this algorithm going to return the answer yes? And if I can get a good estimate of that, it almost feels like I don't need randomness. What I eventually want is if my 0, 1 to the m is the whatever the set of random strings that the algorithm is fed, I just want to get a sense of how often do you say yes, how often do you say no. So it's a very general problem. And this is one of the benchmarks that we will choose to get a sense of how well that algorithm performs, etc. But it's always good to have a stupid algorithm or an obvious algorithm. Okay, what's the first thing that you will do if you are given this task?
Where I have all inputs.
On all inputs is yeah, that is going to be exponential time. At least let's say that I just want an efficient algorithm. Okay, I am okay using randomness. Okay, so the obvious thing is it's called a sampling problem because you randomly sample and then you check what happens. So the obvious algorithm is going to be the following. So this T this is going to be chosen. Whatever, we'll have to figure out what the right value of T should be. So we do some T tries and we just pick an input at random and ask what is the value of f of x, of f of xi. And we just at the end of it, we just count, okay, I made T queries, of which some number of them turned out to be 1, some number of them turned out to be zeros. So the fraction of ones should hopefully be a good estimate of what the fraction of ones are in the entire domain. Okay, this is the first thing that we would want to try. And this is what we will try to match ourselves with. So here is an obvious algorithm. What can I do better in this state? So to get a sense of, we need to really ask the following 2 questions. The first thing is, how many queries did you make to the algorithm? Because that in some sense will tell you something about how much time this algorithm takes. Because maybe this querying f is not an instantaneous operation. F is maybe some complicated machinery whose behavior you're trying to sample. So you would like to make sure that you don't ask the value of f at too many points. Maybe it makes sense to reduce the number of queries. And maybe it also makes sense to reduce the number of randomness that you use. Because hopefully at some point you would want to do this deterministically if possible. Or whatever. So these are 2 questions that we have. So what is the right number of queries?
Log 1 by
Yeah, so this is going to be a version of Chernow's bound. I mean, this is something that we will see in the next class. I presume that you all seen Chernow's bound in one form or the other somewhere. So in the next class, I'll just state down a few probability inequalities that we will use often. But something to just keep in mind very often is that if you want an epsilon accurate answer with probability error at most delta, turns out the right number of queries looks like it's 1 over epsilon squared times log 1 over delta. Okay. This is something that you will see so often in this course that it will become second nature to you. That you will see this 1 over epsilon squared log 1 over delta just showing up every damn time. Okay. So if you choose T to be this value, this 1 over epsilon squared log 1 over delta, Chernoff bound will basically tell you that you are going to be within this accuracy window. Whatever, this mu plus epsilon mu minus epsilon with probability at least 1 minus delta. The chance that you deviate from this window is at most. Okay. How many random bits did we use?
M bits per query.
So it's m bits per query. So that's going to be whatever was m times the number of queries that we get. So it's going to be m times 1 over epsilon squared log 1 over delta. So what we will be asking is we will try and come up with some other schemes, which at the moment it feels like a bizarre thing to suggest. Say, what else can you do besides randomly sampling, the function at various points? So what we will try to do is somehow try and see if either of these can be reduced. Often what will happen is there will be some weird tension that will happen. You try to reduce the number of random bits and you will have to compensate for it by making more queries. And we will try to play this game and sort of somehow say, can I get the optimal answer with respect to how many random bits I need versus how many queries I'm making? And we'll be seeing various examples where one of them we will manage to improve this substantially, but then we will see that this becomes way larger. And then we will say, okay, fine, can I do one more trick to make sure that the number of queries is also not too much, etc. Like for example, Pavel's algorithm, which is just try the function everywhere, the number of random bits is 0. Okay, but obviously the number of queries is 2 power n.
Actually, cannot improve the number of queries.
Yeah, so it will turn out that this is actually optimal. But every time you try to reduce the number of randomness, this queries will shoot up. So we'll try to bring it back down to this thing, because this is something the gold standard. And okay, so that's what we will do. And so finally, I'll just stop with this one example, because this is going to be the first example we're going to see in the next lecture. The notion of max cut. It's a great example to see. We'll see 2 different ways in which we'll get rid of randomness used here. Okay, so let me briefly describe what max cut is. I'm sure people have seen this in some algorithms course or whatever. So given a graph G, and you want to find a cut of largest size. What is a cut? A cut is just a collection of vertices. Once you choose a set of vertices, the cut determined by the set is like how many edges do you have, where one of the endpoints is in the set and one endpoint is outside. So in some sense, if you think of S and S bar, the complement of S as 2 bags of vertices, how many edges are going across this? So in some sense, if S is what you're cutting off, how many edges do you end up cutting? Okay. And you want to choose an S that maximizes this number. Obviously, you can choose one vertex, but maybe there are only 3 edges that are going out of this. So in that case, that max cut is, the cut size is just 3. So we want to ask, amongst all possible cuts that are there in the graph, what is the largest? That's it. Okay. So just formally, these are the edges with one endpoint in S and one endpoint outside S. Okay. Now turns out that this problem is NP-hard. Okay. I don't know if I gave this in the problem set or probably did. Yeah, but this is one of the things that you can show that it is NP-hard. Like finding the optimal cut is actually difficult. So okay, you can ask, okay, fine. Maybe finding the best cut is difficult, but I'm okay with a good enough cut. Okay, is it okay to get an approximation of the max cut? What do we mean by that? We will say that something is an alpha approximation for the max cut. And typically this alpha is, in some places, okay, I'm going to stick to alpha being some number between 0 and 1. Okay, to mean that whatever cut you're outputting is at least as large as alpha times the best cut. So in some sense, the 0.9 approximation is saying maybe the right max cut is some number, but I'm okay if you give me 90% of whatever the best max cut is. I'm willing to tolerate that part. Okay. So this is a problem that's like really, really well studied, in the sense that it's really a question of what value of alpha can you solve? And this is a really important question that is studied. And so what is the silliest algorithm you can think of? Yeah, so the simplest thing to do is basically choose your subset S completely at random. Like every vertex, you toss a coin, decide to either put it in the set S or put it outside the set S. Okay, and so this is like saying that pick a random set, and by random set, what I mean is for every vertex, you make a choice independently, decide to either keep it in the set or keep it outside the set. Okay, So it turns out that this very, very simple algorithm already gives a 0.5 approximation. Okay, we'll do this formally in the next class, but what is a rough intuition? Let's take one particular edge. What's the chance that this is a part of your cut? So for this to be in the cut, you must have decided to put one of these two endpoints inside the set S and one of the endpoints outside the set S. All four possibilities are equally likely. Two of the four possibilities put this edge in the cut, and two of the four possibilities don't put the edge. So on expectation, you will expect half the edges to show up in the cut. Now, whatever your amazing algorithm for max cut is, your cut size can't be larger than the number of edges. And this algorithm, on average, seems to be outputting half the edges. So it's going to be a half approximation. Okay, it's a very simple randomized algorithm that yields a half approximation for max cut. So the first thing that we will do in the next class, after setting up some probability inequalities, just so that we are all on the same page, so that some of you may have seen some inequalities and may not have seen, so that I'll make sure that everybody is on the same page, etc. And what we will do is we just focus on this one stupid algorithm and ask, what did you really need the n choices that you made for max cut? Did you want them all to be independent really? Can you get away with not using independent random choices, but somehow doing something else which is a little correlated, but still get the same behavior? Okay, and we will see two different ways in which you can eliminate the need for randomness in this stupid max cut algorithm. And once we see that, that will then open us for exploring those techniques a bit more. And usually all of this will happen this way. There'll be one problem. In order to solve the problem, you invent some nice technique, and then you start focusing on the technique and say, okay, what else can you do with that technique? And so on. So that's what we're going to see. And for people who want the spoiler, so the two things are going to be limited independence. That's going to be one of them. The second thing is going to be this notion called the method of conditional expectation. Okay, so these are two different ways in which we will see how to de-randomize max cut. And once we come up with these techniques, we'll go back to the sampler question and then ask, oh, wait, we learned some new techniques. Can we use this to build better samplers? And we'll keep on adjusting this back and forth. Okay, so it looks like I ended much earlier than I thought I would be ending.
I see this silly remark. Removing why makes it silly.
Sorry?
Removing the why.
No, I think what ended up happening is like I first wrote silly algorithm and then, this is like public shaming is happening.
Okay, Zoom
and YouTube for internet. The internet doesn't forget.
CBS algorithm.
I will remember master.
CBS algorithm would be output is equal to.
Actually, that's good. See, I mean, there was. So I can only say that this is a silly algorithm. I can't say it's silliest algorithm is output nothing. So that's what we'll do. Okay, I don't want to push more. I certainly didn't write any further here. So in the next class, we will deal with these things in more detail. Look at probability inequalities and so on. But just want to get us in there. How many of you have seen Chernoff bounds or Markov's inequality? Okay. So, but anyway, so I'll just state it. I'll probably not prove them, but I'll just state it in the next class, and then so that we can use that as a takeaway. Okay. So just a reminder to people on Zoom to just add your preferred emails on for what is that thing called? Piazza. For Piazza. Okay, I'll just stop the live stream right now.